Welcome, everyone. Today, we're stepping into the lab and becoming chemical detectives. Our mission, should we choose to accept it, is to solve one of the oldest mysteries in chemistry. What is this unknown substance? And we're going to do it with a toolkit of simple visual tests that help us uncover the secret identities of these compounds. So, just imagine this for a second. Someone hands you a vial. Inside is a perfectly clear, totally anonymous liquid. What is it? Is it an alcohol? An acid? Something else entirely? This little vial, well, that's our crime scene, and we need to start gathering clues to figure out who our suspect is. And this is where our Chemical Detectives Toolkit comes into play. Think of it this way. Every test we're about to look at is like a different tool in our kit. Each one asks a very specific question, and the reaction, or just as importantly, the lack of a reaction, is the clue that's going to lead us to the truth. Okay, so here's our game plan for today. First up, we're going to hunt down some hydrocarbons. Then we'll move on and put some alcohols under interrogation. After that, we've got a classic whodunit, telling aldehydes and ketones apart. And we'll wrap things up with a quick fire round on acids, bases, and sugars. Ready? Let's get started. All right, our first line of inquiry is all about hydrocarbons. And really, we're looking for one very specific, very telling clue, a carbon-carbon double bond. You can think of it as a molecule's unique fingerprint. It completely changes how it behaves. So here's our first tool from the kit. It's called cold potassium permanganate, and it's this really vibrant, deep purple liquid. This stuff is basically our double bond detector. If our mystery substance has a double bond, it'll react, and that beautiful purple color, it'll just vanish. That's a huge clue right there. Now check this out, because this is our detective work in action. It's like we've lined up 3 suspects. First, hexane. We add the purple stuff, and nothing. Stays purple. Totally innocent. No double bonds. Then, toluene. Same deal. That special aromatic ring it has is just too stable to react. But then, look at cyclohexene. The second we add the permanganate, the purple is gone, and we're left with this brown, murky solid. I mean, that is a dead giveaway. The molecule is basically confessing, yep, I've got a double bond. But what if a suspect is being a little stubborn, not giving anything away? Well, sometimes you gotta apply a little pressure. And in chemistry, pressure often means heat. So let's see what happens when we run the same test, but this time, we're gonna turn up the heat. And wow, what a difference a little heat makes. Cyclohexene reacts even faster. But the real plot twist here is toluene. Remember how it did absolutely nothing when it was cold? Well, you add some heat and that purple color disappears. So what's going on? That stable ring is still fine, but that little methyl group hanging off the side, that's its weak spot. The heat gave our permanganate just enough oomph to attack it. And just like that, another case is solved. Okay, let's switch gears and move on to our next class of compounds, the alcohols. Now, the thing about alcohols is they're not all created equal. You've got primary, secondary, and tertiary suspects, and we need to figure out which one we're dealing with. And luckily, our toolkit is perfect for that. A really simple first check is to just see what our alcohol does in water. Take ethanol, it's pretty small, and it mixes with water perfectly. No problem at all. But then you have something bigger, like butanol. It has a longer, kind of greasy carbon chain that doesn't really like water, so it barely dissolves. Right away, this simple test tells us something about the molecule size. All right, now for the main event, the definitive alcohol test. Our tool is acidified potassium dichromate, which is a bright orange solution. And the clue we're looking for is a really dramatic color change. We want to see that bright orange turn into this kind of murky, deep green. Believe me, this one clue is incredibly powerful. So here's the deal. If you add that orange solution to a primary alcohol, like ethanol, or a secondary one, like isopropanol, boom, you get that unmistakable green color. This happens because these alcohols can be oxidized, and that reaction is what makes the orange reagent turn green. It's a positive ID, simple as that. But now watch this. You try the exact same test with the tertiary alcohol, like tert-butanol, and nothing. The solution just stays stubbornly orange. So why the cold shoulder? Well, it's all about the structure. To get that reaction to happen, the alcohol needs a hydrogen atom on a very specific carbon. Tertiary alcohols, they just don't have one. They're too crowded with other atoms. It's like the crucial piece of the puzzle is missing, so the reaction is a complete no-go. Okay, time for a classic case of mistaken identity.
aldehydes and ketones. They're like the chemical world's version of identical twins. They look so similar, but there's a key difference we can use to tell them apart. And the best part? We get to use a tool we're already familiar with.
So we're bringing back our old friend, the orange potassium dichromate, for a little showdown. We test an aldehyde and a ketone. The aldehyde, benzaldehyde, immediately reacts. It turns the solution green. But the ketone, acetone, it does absolutely nothing. Stays orange. This tells us everything we need to know. Aldehydes are easily oxidized, but ketones are much tougher. And just like that, the lookalikes have been unmasked.
All right, let's finish our investigation with a little rapid-fire round. We've got a few more common chemical families to identify, and thankfully, the tests for these are quick, simple, and the results are, well, they're pretty obvious.
So how do you spot an organic acid, like the acetic acid that makes vinegar sour? Easy. You look for bubbles. Seriously, it's one of the most satisfying and straightforward tests in the entire toolkit. And the procedure could not be simpler. You take your sample and you add a little bit of sodium bicarbonate. Yep, just regular old baking soda. If an acid is present, you'll immediately see this vigorous fizzing. All those bubbles are carbon dioxide gas. It's an unmistakable sign you've found an acid. And if you want to be extra sure, you can pull out the classic litmus paper. Just dip a piece of blue litmus paper into your solution, and if it's an acid, it will instantly turn red. Red for acid, it's a simple rule that perfectly confirms what the bubble test told us. And of course, the exact opposite is true for bases. If you think you have a base, like an ammonia solution, you'd use red litmus paper instead. In the presence of a base, that red paper will turn a deep blue. So, blue for base. Easy peasy.
Okay, one final suspect to hunt for, a reducing sugar. Now, don't let the technical name throw you off. All you really need to know is that it's a type of sugar, like glucose, that has a special reactive part of its structure that our next test is designed to spot. Our final tool is called Benedict's reagent, and it's this bright blue solution. When you add it to a reducing sugar and warm it up a little bit, this really cool transformation happens. The blue solution changes, and you get this solid orange or brick red material forming. That's the telltale sign that you have found a reducing sugar. So there you have it, the core of our detectives toolkit. Purple permanganate unmasks double bonds. Orange dichromate is our go-to for certain alcohols and aldehydes. Bicarbonate gives us that bubble test for acids. Litmus paper is the classic acid-base showdown. And Blue Benedict's reagent finds those reducing sugars. Each tool has a very specific job, giving us the clues we need to solve the mystery. So, I'll leave you with a final thought experiment. You have the toolkit now. You test an unknown liquid and it starts bubbling like crazy when you add sodium bicarbonate. You're pretty sure you've got an acid on your hands. So, what's your next move? What's that simple, classic test you'd run just to confirm your theory? The investigation is now in your hands.